Hello everyone, and let's start this video lecture. And this is regarding geometric optics. In the previous video, we have understood how we will be dividing this optics into three parts, and some basic part of ray optics you have understood. So this geometrical optics is also known as ray optics. So in this some basic property of light we have already talked about, like this is speed of light in vacuum is 3 into 10 raised power 8 meter per second. Moreover, this is an electromagnetic wave which is consisting of varying electric field and magnetic field. Moreover, this light is basically something that carries energy as well as momentum, and this v is equal to lambda formula, which is true for wave, is also true for light. And that's another important point, is that these three things make a right hand coordinate system. In these three things, like in speed of this light, that is c, you can say propagation of light. If light moves in this direction, then electric field and magnetic field are mutually perpendicular. So all three are mutually perpendicular and they are in right hand coordinate system format. And the light is basically a part of bigger system which is called electromagnetic spectrum. In this electromagnetic spectrum, this range of wavelength, this is the range of wavelength which is a visible category, which is called light. Okay. And in ray optics, I have told you, like what we do, we talk about the formation of images and all that, and you can recall those points. And what is a ray? We have talked about beam of light. We have talked about the three types: parallel, divergent, and convergent beam of light. Then we said in the ray optics there are two phenomena that are very important. The first one is a reflection of light. In this reflection of light, this light, after getting incident on a medium boundary, it returns back to the same medium. So back to the same medium or medium of incident. So this phenomena is called reflection, you know that. And this can be a plane mirror from where the reflection takes place, or maybe this curved mirror. And these, if the curved mirror are spherical, so we call them as a concave mirror. So concave mirror looks like this. Convex mirror is something like this. And certain terminologies like angle of incidence. So from the normal incident ray, whatever the angle it forms is called angle of incidence. And similarly, reflected light beam from the normal, whatever the angle it makes, that's called angle of reflection. Okay. And this same is true for any type of reflecting boundary, whether it's plane or maybe spherical. So these two are example of spherical mirrors. In these spherical mirrors, we will have either concave, that means if the shining surface is concave, so that's called concave. If the shining surface is outside one, so that's called convex. So angle of reflection you got to know, angle of incidence you got to know. There is something called glancing angle. So this angle, that means surface and this incident ray, whatever the angle they form, that's called glancing angle. And you can relate like this: if you got to know what is the incident angle, you can easily find glancing angle just by using this relation. And then we have already talked about what is the laws of reflections. There are two laws that all three lie in the same plane. All three means incident ray, reflected ray, and normal. And we also know the incident angle is equal to reflected angle. This is true for all the cases, whether it is plane or curved. And there are some special point or important points that you can think of. If incident angle is 0, then if a reflected angle is going to be 0. And this 0 angle is when it falls normally. For instance, this. So in this case, you will find the angle of incidence is 0. Glancing angle is 90 degree, but angle of incidence is 0. Similarly, in this case, this is center of curvature. So from whatever, from where, if the light ray is passing through the center of curvature, so that means you will find normal is also going to be along this line. So you'll find the angle of incidence is going to be 0 because the light rays are normal. Similarly, in this case, you can see. And the important point is, whenever this reflection takes place, then the frequency, wavelength, and speed of the light, and due to reflection, there is no change. They remains the same. However, the intensity of the light changes, and you know the intensity depends on the amplitude, and so amplitude decreases usually, hence intensity decreases, right? So this is some important point related to reflection. Now, if this surface is irregular, and in this case, whatever the reflections are taking place, these kind of reflections are called irregular reflections, which are also called sometimes diffused reflection. So what is a diffused reflection? It's an irregular reflection from irregular surface. Okay, now let's come to this important point called the plane mirror. So how we form the image from the plane mirror and related stuff. So if there is a mirror, plane glass, then you can polish one surface. So this line shows a polished surface, and upside shows reflecting surface. So we draw this kind. This is as a plane mirror, and how the formation of image takes place from a plane mirror. This picture, let me explain to you. So this is a plane mirror M, this bigger one. This is a reflecting face, this is the polished face, this is the object. Let's say this is the object, right? So in order to form the image, what we need to do, we need to find two reflected rays, because we know image is intersection point of reflected or refracted rays. Here the phenomena is reflected, so it has to be the point of intersection of reflected rays, and we know all the reflected rays are going to intersect at the same point. So if we catch any two, we will find the point of intersection. So we usually try to find the easiest ones. So let's say if we consider this as an incident ray, this. So if we consider this as an incident ray, then you'll find there has to be drawn as a normal. So this is going to behave like a normal. So let's say if we are drawing this as a theta 1 angle, then it is going to be theta 1 incident angle. Then theta 1 is also going to be reflected angle. So this beam, this light will be reflected like this, as shown by this line, right? And another light ray you can consider in this one, the one which goes horizontally, and it will be reflected back because it is incident at 0 incidence angle. So these two rays, 1 and 2, you can see that they are not intersecting anywhere in this zone. So what you need to do, you need to produce it backside. You need to produce it backside. Wherever they are intersecting, that is the location of image, right? That is the location of image. Or else what you can do, you can consider this another ray. If you consider this another ray, then you'll find it's going to have a normal like this, then it will be reflected like this. It's a backside production will be meeting at this point. So this will be the point of intersection of all the reflected rays. Hence this will be the location of image. Now you can prove that if this angle is theta 1, this angle is theta 1, so this is going to be theta 1. If this distance is d, this is going to be d. That you can prove. How that d is going to come in, you can say that this is common for the two, and this is 90, this is 90, so they are the equilateral triangle. So this dimension has to be this. So ultimately we remember that if the object is placed here, so you just draw perpendicular, go other side by the same distance, you will find the image location. So from plane mirror, image location can easily be found out using this concept. So steps have been shown over here, you can find it out. So this you can remember, to exactly locate the image, what we can use, perpendicular distance of the object from the mirror is equal to perpendicular distance from the mirror of the image. So object distance from the mirror and image distance from the mirror perpendicularly are equal. For instance, if the object has been shown over here and the mirror is only up to this, then what we need to say, we can produce at the mirror line, and we need to go perpendicular direction to this, and whatever the distance mirror is from the object, the same distance image has to be from the mirror. So if this is d, this has to be d. This is how you can locate the image due to a plane mirror anytime. Now here this is example, you can read this example and you can solve this. So I'm going to just explain what is going on. So it says a mirror is inclined. So this is a mirror which is inclined as shown in the figure, and this is 45 degree from the vertical and horizontal. You can think of mirror starts from origin, so it starts from this point origin, and an object is kept as equal to -2, so that is the location of the object. It is asking that to locate the image. So what do you need to do? Again the same rule, you just produce this mirror. If you produce this mirror and then search what this distance is going to be, so whatever that distance comes out to be, the same distance backside you need to proceed to get the location of image. So if this is 2 and this is going to be 45, because this is 45, so you'll find this is right angled, so these two dimensions are going to be equal, so this will become √2, this will become √2, so this came out to be √2. Since this is coming, d is coming √2, so this is also going to be equal to d, which is √2, and you just move ahead on the same line wherever it meets, that becomes the location of image. Okay, so what the rule goes, you just extend the mirror, drop a perpendicular, whatever that distance is, go backside by the same distance, you'll find the location of image. You can locate it. Now if instead of a point object, if there is a extended linear object, then how to form the image? So you can think of any extended linear object is nothing but a collection of several points, right? So what we need to catch with the extreme points, and once we can catch the extreme points, we can join them with by a straight line. So let's say we have an object, this object is starting from a point and ending at a dash point, and we need to draw this. So what we need to do, first we need to draw the image of this point A, which is going to be, if it is d distance apart, so you just go back d and look at this, this is going to be B, which is image of A. Then come to this extreme point of this object, which is, let's say, a dash, which is distance, a certain distance from this mirror, which is here, and you just go back to perpendicular to this, and here you will be finding another point, you can call it as a B dash. So B dash is image of a dash, B is the image of A. Now this A to A dash was this object, so image will be from B to B dash, so this will become the image location. So if there is an extended linear object, it's going to be very easy to draw. You just catch the extreme points, draw their images, then join this by straight line and put the arrow in the direction it was shown, and that will be there, right? And there are certain properties of the such as image, which is of extended object, that is found from by a plane mirror. So what are those properties? You can see there, the extended object, whatever the extended object is, its size is going to be same as the size of the image. That means the length is going to be same for image as well as for object. And image is erect. Now if this is a mirror, and you've placed the object in the direction or parallel to the mirror, then you'll find the image is also going to be parallel to the mirror. So that means it is erect. It is just like the object. So arrow is upside, so arrow is upside in this case. So that's condition is called erect image, and it happens when it is object is placed parallel to the mirror. So image also comes parallel to the mirror, exactly in the same fashion it is that the object is. Next important point is image is also inverted. That means different. You can see when the object lies perpendicular to the plane mirror. So this is a plane mirror and this is your object. So extended object and mirror, they are perpendicular to each other. Then you'll find it will be inverted. Meaning is this, that if this point is A, then you'll find the image is going to be A dash. If this point is B, image is going to be this B dash. Arrow is from A to B here. Here is going to be A dash to B dash. So you'll find here the direction of arrows are different. Can you see this? The arrow of the object is in this direction, whereas the image in the opposite direction. So this is called inverted image. So inverted image takes place when the object, extended object, lies perpendicular to the mirror, whereas in case of parallel you will find it is erect. So this is important point to keep in mind. Now if you got any object like this, now you can use these two concepts to draw the image of it. So this parallel stuff will remain the same. That means if this point is B upside, so this will be B dash, so this will be image of this. A dash will be image of this. C, which is closer, so it's going to be opposite, it's also going to be closer, C dash. So this is how you can draw the image, and you can think of perpendicular part is inverted, whereas the parallel part is as such, that is erect. Now if we are getting any object like this in this fourth example or fourth point, then what we can do, we can make the components of it. Let's say this is the extended object, which is neither perpendicular nor parallel to this. So in this situation, what we need to do, we need to make two components, one in the parallel direction, another in the perpendicular direction. So we need to make these two components and apply the rule. Which is perpendicular, it has to be inverted, so you just invert it, and which is in this direction, that remains the same, so you just keep that same, and whatever the resultant of these two components is coming, that becomes the final answer. Are you getting this point? So if it is neither parallel nor perpendicular, so you just make the two components using just like a vector. It has been shown over here. This component will be having okay, well, that's a different example, but it follows the same thing. So you can make the two components and then find the resultant that will give you the answer. For instance, if it is here, you can again do what? Parallel and perpendicular. Parallel to this and perpendicular to this. So this perpendicular has to be reversed. So it has to be in this direction. Parallel remains there. So that resultant will come over here. Similarly, can you check it for second example that has been shown over here? You'll find the same rule is taking place there as well to decide the final image of the object by the plane mirror. Okay, here is example number 2. You can read it and you can solve it. Now next point is coming as a field of view. So what is a field of view? You can read it. It says this is the area in which reflected rays exist is called field of view. So that area in which the reflected rays exist, so let's say this is your plane mirror and this is your object. So you consider this the ray which is coming to the extreme corner, and let's get it reflected, so that's a reflected ray. And then consider this ray with, to the extreme corner, this is going to be another reflected ray. So these two reflected rays, extreme rays, so whatever this zone is, that's called field of view. And you can also do that, this you can extend over here, you can extend over here, this will be the image. So it appears like this field of view is coming because of this image, and from here these rays are going like this and creating this field of view, right? Similarly, in this example, you can say this is the object, so consider one extreme ray, another extreme ray, it's a reflection, so these reflected rays are going to create field of view, and it will appear like these rays are coming from this image, right? So based on this, there is one example, it may illustrate this, and you might get similar type of question in exam as well. So it says a man is traveling on the road. So this is a road on which a man is going to travel. Find out the length of the road for which the image will be visible to him. It's just like what is the field view. So whenever the person is going to be in the field view, he will be able to see the image, right? So solution is over here. So what we need to do, let's talk about the solution. Let's say from this O point, consider this extreme way. Similarly, consider this extreme point and reflected ray. And if you want to produce this, you will find this is going to be go and meet at this point, which will be coming as image point, isn't it? And we know if this is object d distance, so this must be d distance, so that will be image. Same picture has been drawn over here, which you can see clearly. So this is d, you can join this point as well, so this is also going to be d. And it says if we consider two triangles, one is a, q and c, so a, q and c, this triangle, you'll find this is a right angle triangle, right? Similarly, we can also catch one more triangle, which is this b, m, c. Here is the m point, let's say m point is there. Now if you consider these two triangles, you'll find they are going to be similar triangles. In this similar triangle, we can apply the property that if this is x, and let's say this point is as placed as a midpoint, so you can consider this is a L by 2. So you will find this x divided by L by 2 is going to be equal to the total distance base, which is going to be d plus d, and this is also going to be d, as we have talked about, because image is just as the same distance as the object from the mirror is. So that's going to be d plus d plus d, that is 3d divided by d. Are you getting this point? So from here you can solve for x. So x came out to be 3L by 2. And just like this is x, you can find this is symmetrical, so downside is going to be the same amount, so that's also going to be x. So total is going to be 2x, which is 3L. So you can check which option is correct. B option is correct option, right? So it says like most of the problems in optics involves geometry and similar triangles, so that you need to brush up, and if you got to know this about this, so this kind of question you can handle. Now in case the object is extended linear, then what is the field of view? So if this is the object, AB object, then you can find the image A dash B dash, right? And once you are able to find the image A dash B dash, so what we need to do, we need to find the point, this field of vision or view for A point as well as B point, right? So and whatever the common is going to be between the two, so that common field of view is called field of view for extended objects. So common field of view of extreme points. So we just catch the extreme point and we talk about it. Okay, next point is the relation between velocity of object and image. So that becomes important question. If the object moves and mirror moves or something happens, then you might be asked about what is the velocity of image. Now we know if we use this coordinate system as shown over here, and let's say mirror is being placed in YZ plane. So mirror is in YZ plane, and perpendicular of this mirror is x direction. So x direction is perpendicular to this, and mirror is in YZ plane. So in that case what happens, right? So if you look try to find the coordinates of this, we know this coordinates in case of x, you will find a minus will come in if we have placed it at origin, and in y coordinates there will be no difference, in z coordinates there will be no difference, right? Now if we know the coordinates, then we know, okay, after after differentiating them we can find the velocity relation. So we are differentiating them with respect to time. So this will be the relation between the velocity along the x direction, along the y direction, along the z direction. Now we can catch them for different way. Now these velocities are coming with respect to mirror, So for x direction, it's going to be velocity of image minus velocity of mirror is equal to minus velocity of object minus velocity of mirror. So we can remember like this: velocity of image minus velocity of mirror is equal to velocity of mirror minus velocity of object. Now if you remember this way, this is true for x direction. For y direction, z direction, they will be having the same velocity as that of the object, because the coordinates are similar, right? So only the x component will have a difference, so that can be understood by this expression, and you can read it. And this is valid, of course, for only for perpendicular component of velocity to the mirror. So x means that component which is perpendicular to the mirror, and parallel component is yz, they remain the same. Now this example will illustrate everything. It says the object with velocity 5 meter per second moves towards the right while mirror is moving 1 meter per second towards the left. So that's object velocity, this is mirror velocity, and you see these velocities are perpendicular to this, so we need to apply this formula. And if you apply this formula, so you will be writing like this. Now you need to place all the values with proper signs. So velocity of image we need to find out, minus velocity of mirror, you can find this velocity of mirror is negative, so you write as a -1 is equal to velocity of mirror, so which is also going to be again -1 minus velocity of object, which is 5. Now if you put these with proper sign, you will find the velocity of image is going to be -7 meter per second. That means it is moving with a 7 meter per second towards left. So you'll find the image will be at this instant somewhere here and will be moving in this direction with velocity 7 meter per second. So this is how the image is moving in this particular example, right? Now example number 5 will let you know, in case the velocity is any direction, then how we are going to solve it. So let's say this is the object. This object is moving at the 60 degree from this horizontal direction, and this 30 degree from this direction, and mirror is moving with velocity 5 meter per second. So this perpendicular direction is important, that means x is important. So what you are going to do, we are going to make the component in this direction, and you are going to make a component in this direction. So 10 cos 60 will be here. So what this 10 cos 60 will become, you know, cos 60 is that you can solve, and then sin 60 will be there, so that will be 10 into half, that is 5, and this will become here 10 into sin, that is root 3 by 2, that is 5 root 3 by 2, 5 root 3. Similarly, you can make the component of this mirror here and in this way. So this will become 5 sin 30. Sin 30 is half, and the cos 30 here you write 5 root 3 by 2. So these are the velocities in x, I cap, j cap directions. So what you need to do, you need to work for x component separately. In x component, apply the formula. Once you apply this formula, what is velocity of image? That is something we are looking for in x direction. What is the velocity of mirror? This is the velocity of mirror that we are interested in. That means it is 5 cos 30. So 5 cos 30 with a minus, because arrow is there, right, is equal to this minus, then velocity of object, this is in the plus direction, and it is 5, or you can write as a 10 cos 60 minus, and velocity of mirror you have already talked about is this amount. After solving this, you can find what the velocity of image is going to be. From here you will find this value coming in. Now along the y direction, you know, it remains the same as the object. And what is that of the object? It does not affected by the mirror velocity in the vertical direction, in that direction it's affected by this. So same, that is 10 root 3 by 2, or you can say 10 cos sin 60. So this is 10 sin 60. So that's another component. And once you got to know these two components, then you can write the velocity of image in proper sense. The first component is I cap direction, the second component is in the j cap direction, and that becomes the complete velocity. So if it is in multiple directions, you can follow this concept. Next point here is the deviation produced by a plane mirror. So this is a plane mirror, and this is an incident light ray that is falling on this. This is a normal, you can see, and this is incident angle. Now if this mirror would not have been there, so this light must have gone like this. So that was supposed to be the direction, but ultimately it's moving in this direction. So from that supposed direction, at what angle it has went, or by what angle it has turned, that angle is called angle of deviation. So angle of deviation is the angle by which the ongoing ray turns up or bends. So this angle is something we are interested in. Now you'll find the entire angle from here to here, it's going to be 180 degree. Out of this, if you subtract this angle, then you will get this del value, right? So this del value is going to be 180 minus I plus I, that is 180 minus 2I. So this is how you can find the deviation. If you know the incidence angle or angle of incidence, you can find the deviation produced by a plane mirror. Here is the example. There's example number 6 solved over here, you can see, and this is example number 7 that you can also see and try to get its answer. Similarly, there is a question example number 8 you can see, and you can solve for it. Now what is a real and virtual object and image? We have already talked about in the previous video, so you can see from there. Another important point is the rotation of a mirror. So if we rotate a mirror, what happens, right? So point is, let's say this is the mirror position initially, and this is the incident ray initially, and we keep this incident ray intact. Now if we rotate this mirror by theta angle like this, so mirror becomes this, new mirror position is this. in this new position you will find you will get a new reflected ray, because normal will be changing from here to here. Initially n1 was normal, so this was your this reflected ray. Now reflected ray will become next, this will become reflected ray because normal has changed. So you might be asked, if you are turning the mirror by theta, by what angle this reflected ray turns up? Reflected ray, this by what angle this turns up? So for a fixed incident ray, if the mirror is rotated by theta, then you'll find this reflected ray turns by 2 theta, right? And how you can see that? You can use this geometry. If you are turning this mirror by theta, normal will be turning by theta, so then you'll find the angle of incidence will become theta additional, and then you need to turn backside, go backside theta additional, so it will become 2 theta, right? So you can remember this as a factual information. So if for a fixed incident ray mirror is rotated by at any angle theta, then you'll find the reflected angle, this reflected ray will be turning by 2 theta. Or we can say, if we are rotating it by omega, so by what angular velocity that will be rotated? So this omega is d theta by dt, this is going to be 2 d theta by dt, that means twice omega. So if you rotate mirror by omega angular velocity, reflected ray rotates by 2 omega, that means double of it. Okay, now let's talk about this image is formed by two plane mirrors. So if there are two plane mirrors, so how we are going to form the images? So first case we are considering when there is a parallel plane mirrors. So if there are two parallel plane mirrors, and let's say this is the object placed in, so what we are going to do, from the first mirror we are going to create the first image over here, so that will be image 1 because of the first mirror. And how much the distance will be? That will be 2 centimeter from here. Okay, and then this image, now this image will be behaving like object for this mirror, so that mirror will be making this image of this image as well. Now for M2 mirror, first of all this object will be directly visible, so you just go by the same amount backside, that means you go this way, and here you will be creating an image by mirror 2 that will be at 8 centimeter. But these are the primary images. Then you'll find the next level images. This image is going to behave like object for this M2. Then you'll find that this total distance is going to be 8 plus 2 plus 2, that is 12. So go 12 centimeter here and look at another image, right? You can call it as this is image after 1 then 2. Similarly, for mirror M1, this is going to behave like an object. So what this distance is going to be, you can count this distance, which is 8 plus 8, 16, and we need to basically count this much, starting from here, this much. So that's going to be 8 plus 8 plus 2, that is 18. So just going 18 centimeter here, you will find another image will be located here, that will be formed by first by mirror 2, then by mirror 1. And similarly you can keep on repeating that this is going to be behave like object for this is going to be behave like object for this, and this cycle will keep on moving. So there will be infinitely many images are going to be formed, and which have been shown on this solution. You can read the solution, and the idea remains this. So you can find these number of images. Okay, then now let's go ahead and talk about the locating the images when the two plane mirrors are not parallel. So they are at certain angle. Let's say this is the case, and the object is placed over here. Then we need to find how many images are going to be there, where they will be located. So for that sake, we can read this number of images found by the two inclined mirrors. So if theta is the angle of inclination, so first of all you are going to calculate this 360 divided by theta. Here theta has to be written in degrees. Now if this number comes out to be even, then you'll find the total number of images is going to be that number minus 1. Right. And if this comes out to be odd, then the total number of images is going to be again that number minus 1, but this is with the condition that this object is placed at the angle bisector, that means in symmetrical conditions. And if this number comes out to be odd, and image is asymmetrical, not at the angle bisector, then the number of images are 360 divided by theta, so one should not be subtracted. And if this is not an integer, then the number of images is the nearest even integer. So this is how you can calculate the total number of images. And how to locate, you can locate in this manner. What to do, you just draw a circle of that radius, and all the images are going to be located on that circle's on the circle's periphery. So you just need to go for the angle. Let's see here, if this is the object, so if this angle is alpha, then you'll find you need to go by alpha this angle, by alpha angle, so this angle is going to be alpha. That will be the first image forming. Now similarly, for this plane, you need to go beta angle, so this is going to be beta, and you will finding the second image. Then after the second image will behave like object for this first mirror, and this total angle will become twice beta plus alpha. So next time it has to go for the twice alpha plus beta, sorry, twice beta plus alpha, because this is beta, so twice beta plus alpha, that means alpha plus twice beta. This will become the new image. Similarly, this for I1, you can see this alpha twice alpha plus beta, so from here it has to go. Now this is going to be behave like an object for mirror M2, and this total angle you are going to read at alpha plus beta, that is 2 alpha plus beta. So from here you need to go by 2 alpha plus beta to get the next image. Is it making sense? So that will be the next image. Similarly, this image will be behaving like object for M1. Measure the angle, go ahead. Similarly, this is going to behave like object for this. Keep on drawing all the objects on this periphery, and you will finding the total number of images from there. And that's called circle concept. You just draw the circle and keep on measuring the angles the way we did over here. You can write all the images, and by using this concept you can find what the total number of images is. Then you are sure how many images you need to plot or draw on this circle. Making sense? Regarding plane mirror, let's consider this last point. This last point says minimum length required to see full image. So if a person wants to see full image, what is the minimum length of the mirror that is required? So answer is height of the person divided by 2. So half of the length or height of the person is required, or observer is required. So it says prove that. Sometime it might ask prove that. So what you need to do, you can think of this as a person, and this person, this is the head of the person, and this is the foot of the person. Okay, and the total height is let's say h or something, or hf we can say. This is the mirror that you have placed in. So what this, and let's say here the eyes are. So you'll find what has to be the happen. This is the head image, this is going to be the foot image. Yes, this ray from the head must go to the eye, this must go to the eye. That is the point. Now so this is the length of the mirror which is required. If the mirror is here, that is of no use. This, if the mirror is here, that is of no use. So the minimum length is going to be this much amount. So this we need to find out. For that sake, you can say if you draw this perpendicular, if you draw this perpendicular, then you'll easily find these two triangles are going to be identical triangles, and you'll find this height is going to be equal to same as this height. Similarly, this triangle and this triangle are going to be identical or equilateral, so whatever this is going to be the same thing. So let's call this as x, this as a y, so this will become x, this will become y. So you'll find that the total height of the person h, if we consider height as h, so it's going to be 2 times x plus y, but the mirror requires is simply x plus y. So mirror is going to be x plus y, and you'll find this x plus y is equal to h by 2. So the required mirror to see the complete image is half of the height of the observer. And similarly, this is example, you can try and you can find your answer using the concept of optics as well as your previous knowledge. Well, so in this video lecture we have talked about the concept related to the plane mirror and how to form the image using a plane mirror. In next video we will talk about the image formation because of a curved mirror, spherical mirrors, or we can call them a convex mirror and concave mirror. Okay, so thank you for watching. Have a great time.